We're going to do the last two problems on that day 2 handout that you have. Okay, ready? There's a few up there if you don't have one. Good. Problem 16 has two annuities working. The first is 12 semi-annual payments of $6,000. First payment's received today. As each payment is received, it's deposited in an account that pays 6.8 annual interest, compounded semi-annually. That's good because the payments are semi-annual. At the same time as the final $6,000 payment is received, you will make the first of 8 semi-annual withdrawals of $10,000. How much will remain in the account at the time the last $10,000 withdrawal is made? So there's the question. What do we have right after the last $10,000 withdrawal? We have a 12 payment annuity. We have an end payment annuity. Both annuities have semi-annual interest payments. So we know we're going to need a semi-annual interest rate. And the interest rate we're given is 0.068 divided by 2, 0.034, and that is a semi-annual rate. The strategy is pretty straightforward. Let's try to get all of these cash flows consolidated at time 18, the time of the last 10,000 withdrawal. And to do that, I'll throw my future value of an annuity equation at the first 12 payment annuity, and we will have $87,113 in the account at time 11. So I want to move, I've consolidated to here, I want to move that amount to time 18. Well, 11 from 18 is 7 years. So we'll use our building block equation, and the $87,000 grows to $110,084.97, and this is at time 18 years. Now all we have to do is consolidate the 8 payment annuity. Its future value is at time 18, where we want to put all the cash flows. So I'll use the future value equation for the $10,000 annuities. There's only 8 payments. And these 8 payments of $10,000 consolidate at time 18 to be a future value of $90,000. And, you know, as a quick check, that's a reasonable number. 8 payments of $10,000 would amounts to $80,000. Well, we accumulated $90,000, so we made about $10,000 interest along the way. Well, we're going to subtract the future value of this annuity because it's really withdrawals. When we do that, we'll have $19,889.33 at time 18. Any questions? Even a problem that looks somewhat complicated, it's just a bunch of simple problems tied together. Okay, let's go on and do our last one. 17 asks us how much must we deposit today in order to withdraw $12,000 at the end of 5 years, $17,000 at the end of 6 years, $20,000 at the end of 8 years, and $25,000 at the end of years 9 through 20. There'll be 12 withdrawals of $25,000 each. They're 1 year apart. Interest is 8% annual interest compounded annually. Okay, so the strategy, of course, is let's bring everything back to time zero. And we're going to begin doing that with these lump sum amounts, and we'll just use our building block equation. That first 12,000, we'll bring it back 5 periods. 17,000 at year 6, we'll bring it back 6 periods. The 20,000 at year 8, oops. We'll bring it back 8 periods. Now we have everything, all these 3 have been put back to time zero. We want to bring the annuity back to time zero. We could do each individual payment, but our annuity equation is going to help us do this a lot more quickly. If I take the present value of these annuity payments, 12 is the number of payments, that's the exponent. I'm going to get some amount of money. Tell me where that amount of money is sitting. Where is that lump sum amount sitting? Where? No? No, but you're thinking, look, here's where the annuity starts. This is the first annuity payment, there's a second, there's a third, there is the 12th. I threw the present value equation at this annuity. I have consolidated the payments into a lump sum amount, a money bag, if you will. Where is that money bag on this timeline? 8. It's sitting right here. And so, I don't know how much it is, but whatever it is, I'm going to take all of it and bring it back 8 periods. Well, 9, wait, I'm sorry. Oh, I'm sorry. I made a mistake. Erase that. The first payment was at year 9, so that money bag's sitting at year 8, and we do bring it back 8 periods. And now we have everything at time zero. We can add all these amounts together. And the present value at time zero is $109,913 and a penny. Okay. Again, a lot of little problems, but none of them were hard. Any questions? All right, this concludes our work with basic perpetuities, where the interest rate fits the time between payments. You've probably noticed that in all of these problems, the interest rate exactly fit the time between payments. In this problem, we had 1 year between payments. We had an annual interest rate. Well, that may not always be the case, and when the interest rate does not fit the time between payments, you will have to manipulate a given interest rate to make an effective rate, which is a simple interest rate, across that time span between payments. And that's what we're going to do now. Okay, this is our third and last lecture. We will work problems today, but after this, we're really going to get our hands dirty and spend the rest of our time working problems together and beginning to really build some confidence in all of these techniques. This third lecture is about manipulating interest rates. Now, there may be several reasons why we might want to create an effective interest rate across some particular time span. We've been given an interest rate with a compounding period that doesn't fit the time span we're interested in. An effective annual rate is equivalent to a simple interest rate. It's just one that we've manufactured. For example, an effective annual rate is the same thing, is equivalent to an annual rate compounded annually. Well, why might we want to do this? We might want to compare two interest rates. They may have different compounding periods. For example, which savings account would you prefer to put your money in? A 0.072 interest rate where it's compounded quarterly, or a 0.071 interest rate that's compounded monthly? We'll solve that one in a little bit. The other reason we might want to build an effective rate is that we cannot use our annuity equations unless we have an interest rate that exactly fits the time span between payments. So we need, if we don't have a simple interest rate across the time between payments, we'll need to manufacture one. And to do that, we'll use interest rate manipulation. Fortunately, it's very easy to do. Now remember that interest rates are usually expressed as annual rates. But unless they're compounded annually, they're really something else. They're simple rates across a week or a day or a month or a semi-annual period. But the equation I'm about to give you will help you to manufacture an effective interest rate across any desired time span. This equation can also be found in your appendix about manipulating interest rates in your primer. And it says that the effective interest rate is equal to 1 plus the stated annual rate, sometimes called the nominal rate. 1 plus the stated annual rate divided by the number of compounding periods in a year. That whole thing taken to a power equal to the number of compounding periods across the time span that we're interested in, across the time between payments, perhaps. We finally subtract 1 to get back to a pure interest rate. So if we have an annual rate compounded monthly, or 12 times per year, you know we're really dealing with a 1-month rate. So we're going to take 1 plus our 1-month rate and take it to a power that expands it across however many months we want. Okay, we might want to expand our 1-month rate across a 6-month rate or a period or across a 1-year period. Well, okay, for example, let's take a 6% annual interest rate compounded monthly and express it as an effective annual rate. So I take 1 plus my stated annual rate divided by the number of compounding periods in a year. There are 12 months in a year. I now have 1 plus my 1-month rate. I'm going to take it to a power equal to the number of months across a year because I want to build an effective annual rate. Then I'll subtract 1 to get back to a pure rate. I can tell you my answer is going to be in the neighborhood of 6%. It's going to be slightly higher than 6% because compounding is going on here. So the rate is 0.06167778. If, for example, I was trying to build an effective semiannual rate, there'd be a 6 here. And the answer would be slightly more than 3%. It'd be 0.0303. So you look at this equation, and it may look like something that's up there to cause you grief and make you memorize. But you know what? I told you once there's only one equation, the building block equation, and that's all this really is. It has its roots in our building block equation. I'll give you an example. You have decided to deposit $1,000 into an account paying 6% compounded monthly. So what do you have in 5 years? Well, our building block equation says we need to move that 1,000 5 years into the future. This is a 1-month rate. So up here I have to have months. Well, in 5 years there are 60 months. Let's see what 1.005 y to the x to the 60th. The answer is 1,000. 348. 85. Now, suppose you go to another bank and they're paying 0.06167778, just the number we found up here. That's an effective annual rate. You put your $1,000 in that account, since this is an effective annual rate, I'm going to use years up here. And we should get exactly to the penny the same amount. Someone want to check me? If it's off, it's a little rounding, that's all. The idea to get from this is that 6% compounded monthly is effectively the same as 0.061178 compounded annually. Should have been a 6 there. Okay? Now you shouldn't have much rounding error at all. Do I have any questions? Because this is something of a difficult concept. We get around to using it, this is where a lot of people make mistakes. So I'll tell you what. If you have your primer, turn to, I think it's page 16. And that appendix is called How to Manipulate Interest Rates and Why. We've already talked about that a bit, but if you read this very slowly, 1 or 2 times, it will just reinforce what you already know. On the next page is the equation that I wrote out for you. And below that we have some practice questions. So why don't we try to tackle some of them? The first question says you want to find the present value of a stream of semi-annual payments using an interest rate of 0.094 compounded weekly. Oh, okay, so our interest rate is really a 1-week rate. And the problem is that we have a full 6 months between payments. The interest rate that we've been given only spans a week, a very short period of time. We need to build an interest rate that spans the whole 6 months. And when I look at this, if the stated annual rate's 0.094, I'm going to bet you the interest rate we create is going to be about half of that, 0.047 plus some for compounding, and maybe 0.048 or 0.049. But we're going to do it the same way every time. The formula says take 1 plus the stated annual rate, 0.094, divided by the number of compounded periods in a year. Now take that to a power equal to the number of compounding periods, weeks, across 6 months. How many weeks in 6 months? 26, 52 in a year, 26 in a... Oh, Boy, somebody, yeah. Okay, we're right. Compounded weekly, 26. Subtract 1 to get back to a pure interest rate. Let's see how this works. And I get 0.048077, a little more than half of 0.094, about what we suspected. The next problem says that again we have semi-annual payments, and again we have 0.094, but this time it's compounded daily. But we're going to approach it exactly the same way. We take 1 plus the stated annual rate divided by 365 days in a year. Well, how many days in a half of a year? Well, how about 182? This won't make that much difference, but I'll put 182 and a half. And while these are going to be dealing with real little numbers and real large exponents, I'm still going to come out with a rate that's a little bit more than 0.047. Is it going to be higher than this rate right here? Should be. Compounding weekly is more daily, a little more than compounding weekly. Very close to the same, slightly higher, as you might expect. Okay? Questions? Anyone? And next problem, we have a stream of 3-year payments. In other words, our payments are now 3 full years apart. But the interest rate is 8% compounded monthly. And we need an effective 3-year rate. Well, we don't see 3-year rates very often, but there is no law that says we cannot build one. So we take 1 plus our stated annual rate divided by the 12 compounding periods in a year. And how many months are in 3 years? Well, 36. I'm looking for a rate something in the neighborhood of 3 times 8. Plus, I expect quite a bit for compounding. And the answer is 0.27. Okay? They're all the same. They're all the same. The next one, weekly payments, 0.076 compounded daily. We've got to build an effective 1-week rate. So I'm going to take 1 plus my 1-day rate. And that's 0.076 divided by 365. So I've got 1 plus a 1-day rate, and I want to expand it out how many periods? 7. 7 days in a week. Now, this one is a little bit too small for me to estimate, so I'm just going to trust my calculator. 0.0 3.76 divided by 365 plus 1, and y to the x and hit a 7. Is that correct? Gonna hope so. And the next one, we should be getting bored by now. This is so easy, right? Here we have 0.062 annual rate, compounded quarterly, and we want an effective annual rate. So what's the power here? Annual payments, I need an effective annual rate. 4 quarters in a year. And I better get something like 0.062 plus, a little bit. I'll just think about the challenge problem a little bit, but it's basically asking you to take an effective annual rate and shrink it. We'll pick that up later if I get a question on it. Okay, you see the procedure, and it ought to begin to get almost intuitive. But when we need to manipulate an interest rate, we'll apply this procedure. And it's done the same way every time. I've given you something called Day 3 problems. These are from the primer. Then I've blown them up a little larger. At this point, you can work every problem in the primer. You have all of the tools to do it with. I'm picking out 3 here that are kind of complex. We'll work them. I hope over the weekend you'll take as big a bite out of the problems at the end of your primer as you can. When we come back next week, we're going to just sit here and work problems together. All right. I'll try to do these kind of thinking aloud. I think it's always a good idea to try to draw yourself a picture of the problem. And if you do that well, you can pretty much solve the picture instead of keep going back to the problem. So let's try to do that first. Oh, well, I want one other change. I want you to make a little change in this. Instead of being interest rate compounded annually, let's change it to monthly so we can practice our technique. Our answer will be close but a little different from. You deposit $3,000 today, $3,000 at the end of each year for 5 years. That means 6 deposits of $3,000 each. We also noticed there was 1 year between them. You wish to begin making 6 annual withdrawals of $3,000, with the first withdrawal being made at the end of year 8. So right here. 3, 4, 5, 6. How much money will remain in the account at the end of year 13 when the final withdrawal is made? It's kind of similar to the one we just did, actually. But we have the added problem that there's a year between payments, and our interest rate is a 1-month rate. So before we even start strategizing, let's change that 1-month rate to an effective annual rate. And we're going to do that by taking 1 plus the stated annual rate divided by the number of compounding periods in a year, taken to the number of compounding periods between payments. It's going to be a little more than 0.065. There's the rate we're going to use in our annuity equations. And I think our strategy, of course, is let's try to get all of these payments to time 13. I'll start by taking $3,000. Use the future of the $3,000 6-payment annuity. I'll use my future value. And we'll consolidate at some amount right here on top of the 5th payment. Well, the future value I got was $21,296.73, and I know that's at time 5. Well, now I think I'm just going to move it over here to time 13. I've built an annualized rate, so why not use it? Five from 13 is 8, so that's an 8 years. I want to move it forward in time. Annual rate, 8 yearly periods. We'll end up with $35,771.46. Now, of course, we could have used our building block equation like this, too. I could have used 1 plus 0.065 over 12. What have I done? Again? All right. We learned last time how to fix this. When did I do it? How long ago? I'll try to Huh? Just okay. All right. We could also use our building block equation with our 1-month rate. Of course, our exponent has to be in months. And in 8 years, there are 96 months. And I'm willing to bet you will get the same answer exactly. So, at this point, we've taken our deposits. We've moved them to time 13. Let's take away our withdrawals. The future value of 1, 2, 3, 4, these 6 payments Well, we worked that a little earlier, so we know what it is. And we're taking this away from 35,000. We've got both. We've got the 35,000. We've got the 21,000 at the same point in time. Now I can take one from the other, and the answer is 14,474.72. And notice that making that interest rate compounded monthly was helpful to us. Our future value was higher. More compounding is good for savers. Any questions on that problem? Here's a perpetuity. But it's a strange one because the payments are 5 years apart. It's also a problem you may run into in your corporate finance course if you're ever comparing capital budgeting projects with unequal lives. But we're just going to focus on the cash flows here. The problem says you will receive $5,000 at the end of 5 years, 10 years, 15 years, etc. forever. So the timeline there are 5 years between the payments. So for us to solve this, we need to create an effective 5-year rate. If interest is 12% compounded annually, again, the same thing every time. 1 plus the stated annual rate, the number of compounding periods per year is 1. I'm going to take it to the 5th power because there's 5 years between payments, and that's the compounding period. And you know, 5 times 12 is 0.6. I'm expecting something in the 0.6 neighborhood, but in over 5 years, there's a lot of compounding going on. So let's see. Actually, we get 0.76. 2, 3, 4. And that is a 5-year interest rate. We want the present value of the perpetuity. And the perpetuity equation payment divided by the interest rate will consolidate all of these payments into a lump sum amount 1 period before the first payment. What is the period in this question? When I say 1 period before the first payment? The period is 5 years because there's 5 years between payments. Any questions? Anyone? I have a question for you. What if the problem had said you will receive 5,000 today and 5,000 at the end of 5 years, 10 years, 15 forever? What would the answer be?
Well, I don't know. I have a question, but I don't know the answer.
I bet you do.
What was the question?
All right, my question first. If this problem said you will receive $5,000 today, and then $5,000 at the end of 5 years, 10 years, 15 years, etc., what would the answer be? Well, without the $5,000 today, the answer is $6,500 something. If you got another $5,000 today, add it to the $6,000, $11,000. We had one like that earlier. What was your question?
My question was, what is the 65, 58, 73, what does that represent?
That represents the value of those payments. If I told you, or you told me, you know, interest is 12% compounded annually. That's what I think money's worth. And I told you, well, you know what, I'm going to give you $5,000. The first payment will be in 5 years. I'll give you another $5,000 in 10 years, another $5,000 in 15 years, and we'll do this forever. Your children, their children, $5,000 every 5 years forever. And you'd tell me, you know what, I just as soon sell that for $6,558.73. They're both equivalent to me, given 12% annual interest compounded annually. And to satisfy yourself of that, let's just see. Let's suppose we had $6,558.73. We put it in this bank account, 12%, compounded annually. And 5 years later, what would we have? I'm going to bet, you guys do it, but I'm going to bet you have $11,558. Am I right? Somebody? Yes? Good. And so, you see, you could take your $5,000 out of that account, you'd be left with $6,558, and it could earn interest over the next 5 years and grow to $11,000 again. Sometimes you really have to trust your calculators and trust your mathematics, because just looking at that, you think, oh man, would I trade $5,000 every 5 years forever for $6,000, $500 today? Well, if interest rates are 12%, you'd be indifferent to that trade. Question? Okay, we're moving along today. And question 26 in the primer says, what is the value today of 20 equal semi-annual payments of $8,000? If the first payment is to be received at the end of year 10, interest is 8.5% compounded quarterly. There's 6 months between payments. Now this was one we did. We didn't have to manipulate the interest rate, but we did something like this yesterday. And I think I told you that most classes find this to be a tough problem. But let's think about all of our time value rules here. Our strategy, since I'm not sure, I could count on my fingers and find out where these end. I think they end at time maybe 29, but I know where they begin. First payment is at time 10. So I think my strategy will be to put the present value of an annuity equation on these 20 payments, consolidate them, and then move them to time 0. But before I can use my annuity equation, I need an effective 6-month rate. Well, what we're given is 0.085 compounded 4 times per year. We're given a quarterly rate. So 1 plus my quarterly rate, what goes up here to expand that to semi-annual? 2. Subtract 1 to get the interest rate back. What answer are we looking for? About 4.25%, plus a little bit for compounding. That's what we'll put in our annuity equation. Our strategy is to consolidate the annuity payments. There are 20 payments, so 20 is the exponent. And I get 105,935.48. But where? At year what? Where in the timeline is this lump sum amount? Where? 9? Like year 9? 9 years, 6 months. Because the period between payments is 6 months, so the first payment's in 10 years, we go 6 months earlier, 9.5 years is where this 105,000 is sitting. Now I can bring it back to time 0. I've built a semi-annual rate, so I'll go ahead and use it. If this is a semi-annual rate, I must have semi-annual periods. So what do I want for my exponent here? 19. 9.5 years. 9 years is 18. One more, half a year, 19. Does anybody check this? And the answer, well, is 47,645.60. What now?
The second part, where it says present value of 10 equals 0, shouldn't that be at the top? It should be 105,604.
Oh, I have 104. I'm sorry. It's this number here. Should be 105. Is that what? Okay, thank you. Okay. Any questions? Are we beginning to feel a little, confident about these things? I don't know how many of them you've attempted on your own yet, but that's really the way you learn it. You've got to sit down and work them. Right now, you've got that primer with the appendix, and you have answers correct to the penny. You don't have to be correct to the penny, but you have to have a correct procedure to get close. And that's going to take a little bit of work. And hopefully you'll work at home, but we will definitely work here. We'll work together. We'll see our mistakes, and that's one way you learn. It has been my observation, working with a lot of students, that often the understanding of this sort of comes in a flash. One minute you don't know it, and the next minute bells are ringing and lights are flashing, and what used to seem difficult begins to seem very easy. And then you get to the point where you say, he can't trick me. I've seen everything he's got. Bring that test on. And that's the way I want you to be. Let's look at one last one. This one is taken from your time value spreadsheet. You have several, and they can be found in the GLab temps. If I could get this to work. And I think this one was problem number 4, but there's 8 problems there for you. And I'm going to change this problem to be like the one in your handout. The payments were $500, so I'll just change that payment to $500. You'll see it changes from 3 to 500 up there. The interest rate was 0.08, so I'll change that. It was compounded quarterly, so I'll put a 4 here. There were 12 deposits and 26 withdrawals, so that's fine. So once you have your problem set up, you can solve it. And then you can look over on the next page to see the answer. Well, first let's look at this question and see if we know the strategy. You've decided to make equal annual deposits of $500 to an account that pays 8% annual interest, compounded quarterly. So you have annual payments, but a quarterly interest rate. You plan to make 12 deposits, first today, the last at the end of year 11. 6 months later, you will make the first of 26 semi-annual withdrawals. Oh no, we've got an annuity with annual payments and another annuity with semi-annual payments. And it says, how large can the withdrawals be? This is one of those problems where all of the money flowing into the account is equivalent to all the money flowing out of the account. You can pick any point in time on the timeline and use it as your consolidation point. So there are many ways to work this problem besides the way that I'm working it on the next page. Basically, I decided to work it this way. I said, well, we have an effective annual interest rate, and of course, if you look at that, you can see how it was calculated, but you know how it's calculated. We have an effective semi-annual interest rate. And I think I should have more, more decimals really. So what I did first was find the future value of the 12 deposits at the end of year 11. Then moved it to the end of year 24. And then if I did move it to the end of year 24, I must have used the future value equation to move this annuity to 24, and found that the size of the payments could be as large as $604. See, I guess what I'm saying is you could have brought everything to here and made this lump sum equal to the present value of the unknown annuity. I took it from here to here, made it equal to the future value of the unknown annuity. Two different ways to solve the problem, but only one correct answer. 7 more problems, have a shot at them. And you can make new problems out of this too. All right, I want to thank all of you for coming. And I'm looking forward to us really getting our hands dirty and working next week. We've been filming this, you've noticed, mainly for our Hong Kong students, our Hong Kong MBA program. I've taught in it a few times. I hope someday to be back there. We usually teach our course in the winter. So you Hong Kong students, I hope you'll come to Cedar Falls someday, but you may not want to come for December graduation. I've asked the cameraman to take us away by taking a little shot of campus where it is what? 7 below zero this morning? And we're not talking Celsius? That's about 20 something below Celsius. I'll see you Tuesday, guys. Thanks.